Okay, so let's set the scene. Physics. Late 1800s. It felt kind of settled, didn't it? Mostly Newton.
Yeah, Newton's laws seemed to cover almost everything. But there were these little nagging problems.
Especially around light, right? It was behaving strangely.
Exactly. People were doing experiments like Michelson-Morley trying to find this aether, the stuff they thought light waves traveled through.
And they just couldn't pin it down. Nothing. Light was being stubborn.
It really was. It felt like physics was sort of stuck.
And then this young guy working in a patent office in Switzerland.
Albert Einstein.
Yep.
In Bern, 1905, he puts out this paper on the electrodynamics of moving bodies.
And it just turns everything upside down. So our mission here is to really dig into the sources on special relativity, understand its core ideas and what they mean for, well, everything.
Absolutely. And it really starts with two incredibly bold ideas, postulates he called them.
Okay, what's the first one?
First, the laws of physics are the same for everyone as long as they're moving uniformly. Constant speed, no acceleration.
Right, like physics works the same whether you're on a smoothly moving train or standing still on the platform. That kind of makes sense.
Yells intuitive, yeah.
Yeah.
But the second one, that's the kicker.
This is the one that twists my brain. Go on.
The speed of light in a vacuum is constant for everyone. It doesn't matter how fast the light source is moving towards you or away from you or how fast you're moving. You'll always measure it at the same speed.
Wait, how is that even possible? If I'm running towards a flashlight, shouldn't the light seem faster?
You'd think so based on everyday experience, but no. And because that speed must stay constant, something else has to adjust.
What gives?
Our concepts of space and time. They're not fixed and absolute like we thought. They have to be flexible to keep light speed constant for all observers.
Okay, so space and time themselves have to warp? That's wild. What are the big consequences that come out of this? Our sources must highlight some.
Oh, definitely. The most famous is probably time dilation.
Time dilation. Moving clocks tick slower.
Exactly. Compared to a clock that's stationary relative to you. And it's not just a theoretical idea. The sources mention it's been proven.
Oh.
With incredibly precise atomic clocks. They flew some on airplanes, kept identical ones on the ground when the planes landed.
The clocks on the plane showed less time had passed? Seriously.
Seriously, a tiny amount, but measurable. Time literally ran slower for the moving clocks. It's why the twin paradox thought experiment works. The space-traveling twin comes back younger.
Wow. Okay, so time isn't universal. It depends on your motion. What about space? Does that get weird too? Or contraction?
That's mentioned too. It's connected. If you watch something moving very fast, close to light speed, it looks shorter. Squashed, kind of, but only in the direction it's moving.
So a speeding spaceship would look flattened from the side.
From your stationary perspective, yes. Is another consequence needed to keep that speed of light constant for everyone? Space and time adjusting together.
Okay, space and time are relative, linked. Then there's the big one, E, MCFT. How does that equation fit into all this? It feels different.
It might seem different, but it falls right out of the same framework. The sources make it clear. It reveals that mass and energy are essentially the same thing, interchangeable.
Mass is energy.
And energy has mass. They're two forms of the same underlying stuff. That equation tells us how much energy is locked up in a certain amount of mass. It's fundamental to understanding nuclear power, stars, the universe itself, but it comes directly from relativity's principles.
So the big picture then, space and time aren't separate, not just a background stage.
Exactly. Einstein showed they're woven together into this four-dimensional fabric called spacetime.
So spacetime, okay.
And get this, within spacetime, even the idea of two things happening simultaneously is relative.
What do you mean?
Well, two events that look like they happen at the exact same instant for me might happen at slightly different times for you if you're moving relative to me. There's no single universal now.
Mine. Blown. Okay, so wrapping up. Special relativity, based on those two postulates, changes everything about space and time, but it applies specifically to uniform motion, right? No acceleration.
That's right. It set the stage for general relativity later, which tackled gravity and acceleration. But special relativity was the crucial first step.
Its impact was just immense. It reshaped physics, showing space and time are relative dynamic, connected.
Fundamentally connected.
So let's bring it back to you listening. What does it actually mean that time isn't some universal clock ticking the same for everyone, that it literally depends on how fast you're moving?
Yeah, and it leaves us with this thought, just based on what we've discussed. If things we think are totally concrete, like how long something is or how much time passes, if those can actually change depending on your perspective, your motion, well, what else about reality might be more relative, more dependent on viewpoint than we usually think.